Welcome to the Explainer. Right now, all around us, there is a fascinating, completely invisible battle going on against a silent, destructive force. Whether we're talking about a massive industrial generator, a delicate aerospace instrument, or honestly just the smartphone sitting right there on your desk, meticulous engineering is literally the only thing stopping our modern world from shaking itself to pieces.
So think about this for a second. How do the world's most powerful machines survive their own destructive energy? An engine produces incredible rotational force, right? An aircraft blasts through heavy atmosphere turbulence. All of that power generates massive internal kinetic energy. If that energy goes completely unchecked, it doesn't just make a loud, annoying noise. It tears metal apart, it snaps circuit boards, and it will absolutely destroy the very machine that created it.
Here's the roadmap for this explainer. First, we'll dive into the threat of kinetic chaos. Then, we'll break down how unwanted vibration actually works. Third, we'll look at the invisible shield of vibration isolators. Fourth, we'll zoom way down to secure the microworld. And finally, we'll wrap up with why protecting all these components is an absolute game changer. All right, part one, the threat of kinetic chaos and the physical toll of unchecked vibration. You know, when we talk about vibration, we usually just picture machines breaking, but it's actually much worse than that. Vibration causes severe, lasting harm to the human body. When operators are subjected to prolonged exposure on the job, the effects are just devastating. We're talking about hand-arm vibration syndrome, or HIVS, severe musculoskeletal disorders, permanent nerve damage, and hearing loss. So the stakes for taming this chaos aren't just financial, they're deeply human.
Moving right along to part two, understanding unwanted vibration, or the physics of this invisible threat. So what are we actually fighting here? In engineering physics, we're basically facing two main enemies, sinusoidal versus random vibration. Sinusoidal vibration is predictable. It's that steady, rhythmic hum of a reciprocating engine. You know exactly what's coming. Random vibration, on the other hand, is pure chaos. Think of an airplane getting battered by heavy turbulence. You can't predict every single bump, so you have to engineer for statistical probabilities. And that brings us to the absolute nightmare scenario in physics, resonance. Every system out there has a natural frequency. The rate will vibrate when disturbed on its own. But if an external force hits that system at the exact same frequency as its natural frequency, boom, you get resonance. The vibration's amplitude skyrockets. It's kind of like pushing a kid on a swing at the exact right moment, except instead of the kid going higher, the entire swing set explodes. Resonance is the ultimate enemy of stability, and we absolutely have to defeat it.
Which brings us to part three, how vibration isolators work. This is where we build that invisible shield.
Let's start with passive isolation. It is wonderfully simple but incredibly efficient. A passive system relies on three parts. First, the isolated mass. That's the payload you want to protect. Second, a spring or flexible material. The mass, combined with that spring's stiffness, creates a brand new natural frequency to soften those incoming hits. And third, a damper, which literally absorbs and neutralizes that destructive energy.
Now, the materials we use for this are super specific to the problem we're trying to solve. Rubber, for instance, is viscoelastic, meaning it gives you both elasticity and damping, which is perfect for your car's motor mounts. Then you have wire rope made of helical steel cables. It's incredibly tough and heat-resistant, making it perfect for fighting unpredictable random vibration. Coil springs, that's the oldest trick in the book, great for steady sinusoidal vibration. And finally, oil dampers are used to reduce that dreaded resonance magnification in highly specialized systems.
But hey, what if passive just isn't enough? Enter active isolation. Unlike passive systems that just sit there and absorb energy, active systems actually fight back. They produce an independent force to cancel incoming vibrations entirely. Using a controller, a piezoelectric accelerometer, an electromagnetic transducer, and a feedback circuit, this system actively monitors and counters movement. It's definitely more expensive and complex, but if you're doing hyper-precise scientific work, like running an electron microscope, it's absolutely essential. Let's bounce back to those passive wire ropes for a second, because the physical geometry of an isolator is a huge deal. Engineers have to shape the wire rope to fit very specific spaces and loads. Take the SB series. It uses a compact structure with shorter bars specifically for tight, confined spaces. Meanwhile, the XM series uses this symmetrical X shape that gives fantastic vertical strength and torsional resistance for lighter loads. The environment literally dictates the geometry of the protection.
All right, part four, securing the micro world. Let's zoom way in on electronic fasteners.
So we're moving from massive industrial physics to the tiny components inside your devices. These little nylon supports hold printed circuit boards tightly to a chassis. Think of them as a microscopic equivalents of those giant industrial isolators we just talked about. They are silently keeping your delicate circuitry insulated from the harsh realities of the physical world.
Look at the sheer variety here. You've got everything from intricate snap-lock mechanisms to straightforward tubular spacers. And the genius part? The vast majority of these supports are designed to be installed completely by hand. No heavy assembly equipment required. You literally just push them into place, and they secure the whole board.
And here's where it gets really interesting. A tiny tweak in mechanical design totally changes a technician's day down the line. A snap lock is pushed through a hole and snaps open, but to remove it later, you have to physically squeeze or pinch the device. A snap fit, on the other hand, also pushes through and snaps open, but to get it out, you just pull or push. No pinching required. It's a tiny detail, but a huge deal for maintenance.
Just take a second to process this massive, hidden inventory of parts needed to build modern electronics. We're talking about an unbelievable array of hardware. Card guides for circuit racks, blind hole rivets, unscrewing rivets, push-in latches, cable ties, the whole shebang, all working continuously together in the background to stop things from shaking apart.
Now you might be thinking, it's just plastic, right? Absolutely not. Material science is critical, even at this microscopic scale. For your everyday applications, general-purpose nylon 6/6 does the job just fine. But when engineers are dealing with extreme kinetic energy, they have to switch to impact-modified nylon HB. It's specially formulated to survive severe shear forces that would otherwise snap a standard support right in half and ruin the board.
Which leads us to our final section, Part 5, Why Component Protection Matters and the True Cost of All This Kinetic Chaos.
So why do we go through all this trouble? Well, by stopping vibration, whether we're using a massive steel wire rope or a tiny plastic snap fit, we're doing so much more than just saving a single screw. We're massively improving operational efficiency and making equipment last longer. We're enabling highly precise scientific breakthroughs that would otherwise be impossible. We're making transport safer over turbulent terrain. And yeah, from a business standpoint, we are driving a massive reduction in maintenance costs. It literally saves whole missions.
I love this quote from our source material because it just hits the nail on the head. Prolonged exposure to vibration contributes to mechanical wear and tear. Reducing unwanted vibration improves a device's longevity. That perfectly distills the ultimate goal here. Conquering vibration at every single scale is the absolute key to mechanical immortality.
So, here's a thought to leave you with. Next time you turn the ignition in your car or fire up a heavy-duty washing machine or even just open up your laptop, ask yourself, what invisible, meticulously engineered components are silently fighting a war against chaos right this very second just to hold it all together?